Hello friends, now this one is the last video for the beam problem, and I quickly explain the one numerical questions for the beam problem. So this one is the numerical questions, problem number 1. For the beam and loading shown in the figure, determine first slope at 2 and 3, and second part the vertical deflections at the midpoint of the distributed load. That is, the you have to find the deflections at the midpoint of the distributed load. So this one is one end the fixed and another is the simply supported, and fixing moment m1 is generated at node 1, and r1 is the reactions at node 1. Length of this length is 1 meter, and this length is the 1 meter. Element 1 and 2, UDL load is the 12 kilonewton per meter. E Young modulus is the 200 gigapascal, and moment of inertia I is equal to 4 into 10 per power 6 mm4. So first EI by LQ is equal to 200 into 10 per power 9 into 4 into 10 per power minus 6 divided by LQ. This becomes 8 into 10 per power 5 Newton per meter. And element stiffness matrix is the same for the element 1 and 2. So KE1 is equal to KE2 is equal to EI by AQ, 12 6a minus 12 6a 6a 4a square minus 6a 2a square minus 12 minus 6a 12 minus 6a 6a 2a square minus 6a 4a square. So KE1 is equal to 8 into 10 power 5. Already I find the value EI by LQ, and this one is the value A is the 1 meter, so multiplied 1 in each, so this becomes 12 6 minus 12 6 6 4 minus 6 2 minus 12 minus 6 12 minus 6 6 2 minus 6 4. And similarly for the element 2, element stiffness matrix will be same, 8 into 10 power 5, and this one is the element stiffness matrix. But there is the difference between the degree of freedom. The degree of freedom for the first element is the 1 2 3 and 4, 1 2 3 and 4, but the second 3 4 5 6, 3 4 5 6. Now assemble, already I discussed in previous questions how can assemble. So make a global stiffness matrix. Degree of freedom of the global stiffness matrix, it has the 3 nodes, so total degree of freedom becomes the 6. 1 2 3 4 5 6, 1 2 3 4 5 6. For element 1, this one is the 1 2 3 4, and up to this points. This is the for the element 1, and the for the element 2 will be added from 3 4 5 6. So this one is the 3 4 5 6. So this one is the element 2. Element 2 is highlighted by the green highlighters. And after assembly, this one is the final stiffness matrix, global stiffness matrix. And when we multiply the w1 theta, this matrix, w1 theta 1, w2 theta 2, w3 theta 3, and this this multiplied by this is equal to force matrix. So separately I evaluated the force matrix. So fe1 is equal to, this one is the 1 2 3 4, and fe2, that this one is the distributed. Here there is no distributed load, so 0 0 0 0 for the element 1. For the element 2, we use the previous formula for the distributed load and evaluated the force matrix for the element 2. And this one is the this final force matrix. For the final force matrix for the distributed load, this one is the for the element 1 0 0 0 0. For the element 2, 6, 1, 6 or minus 1, and this one common is 10 to the power 3, plus force matrix due to the point loading, that is the due to the point loading reactions and moment. So reaction is R1 M1, R2 0 and R5 0. So the final, this is the force matrix R1 M1 6 plus R2 1 6 plus R5 and minus 1 plus 0. So if apply the boundary conditions, already boundary conditions is shown in the figures, that is the first degree of freedom 0, so first row first column 0, second degree of freedom is 0, second row and second column is 0, and this one is the bond. This one is the here at this point deflection is 0, so third degree of freedom, and for this point fifth degree of freedom becomes the 0. So third row and third column becomes the 0, fifth row and fifth column becomes the 0. So remaining terms we will write the remaining terms. This one is the remaining terms. This one is the remaining term 2 by 2 after applying the boundary conditions. This term is the 8 into 10 to the power 5, 8 2 2 4, theta 2 theta 3 is equal to minus 1 1 into 10 to the power 3. So from solve both equations and we can get the theta 2. This one is the theta 2, theta 2 2.679 into 10 to the power 10 to the power 5, and theta 3 is equal to 4.4645 into 10 to the power minus 4. And we have to find the deflections at the middle of the UDL load. So this one is the denoted by V, there is W, so sorry, W. So W is equal to N1 N2 N3 N4 for the second element, W2 theta 2 W3 theta 3, and this one is the N1 N2 N3 N4. W2 is the 0 theta 2 and W3 is the 0 and theta 3. So W is equal to N2 theta 2 N4 theta 3. For the we can write the N1 N2 N3 N4 from the previous equations already derived at the starting of the in the theory portions. So N1 is equal to 1 minus 3 R square by A square 2 R cube by A cube. N2 similarly R minus 2 R square by A plus R cube by A square. N3 2 R square by A square minus 2 R cube by A cube. N4 is equal to R cube by A square minus R square by A square. And here for the midpoint R is equal to A by 2. So N2 becomes, this one is the A by 8, and N4 becomes minus A by 8. And when substitute the values, so you can get W at the middle point is equal to A by 8 theta 2 plus minus A by 8 theta 3, and this value is 0.08928 mm. In the books it is solved by the different method, so you can also follow the method which had used in the books. Next already I have discussed these questions, but quickly I discuss this again this questions. This one is the fixed beam, and Q naught is applied in the downward directions. P force is a point loading. M naught is the bending moment. L by 2 is the total length is L. L by 2 is the element length. So this one already explained in the previous video. KE1, this one is the element stiffness matrix for the element 1, and this one is the element stiffness matrix for the element 2. And this one is the global element stiffness matrix, and K into delta is equal to this one W1 theta 1, W2 theta 2, W3 theta 3. This one is the global stiffness matrix. Next, after applying the boundary conditions, first row the W1 theta 1 0, W3 theta 3 is equal to 0. So first row, first column 0, second row, second column 0, fifth row and fifth column 0, sixth row and sixth column 0, and this one is the force, right side force matrix. So when you solve it, so you can get the 2 by 2 matrix, and theta 2 in this one, and W2 is equal to this one. And when substitute use this one, first one, so you can get the value of reactions Ra. So E by Ei by Aq minus 12 W2 plus 6A theta 2 Q naught A by 2 plus Ra. So you can get the value of Ra from these equations. So this one is the two solve example I have discussed for the beam chapters. Some assignments will be given in the notes, so you have to solve the assignment, and any doubt, if you feel any doubt, you can write to the CR, and he will ask from from me, and I will give the solution or give the any doubt, I will clear it. Okay, thank you for your patience. Okay, thank you.